I didn't get your name, but
Jay.
Jay, thanks for the introduction. This is me on Twitter. If you have any questions, feel free to ask them later, and I can get in touch. Otherwise, we'll try and, if I time things right, we'll have time at the end to get to some conversation. So I work in the New York office with these guys. The guy in the middle is turned around, so he does actually have a face. We work on the PHP driver, so I had a few sessions upstairs today for that. And additionally, to the PHP driver, I also work on an ODM for PHP as well. And then before coming to MongoDB 2 years ago, I had used it for 2 different companies beforehand. So I had a good amount of experience writing applications with it before coming to the company. So the topics I want to cover today, this is going to be like a best practices talk. I don't know if we didn't bring any for this, but how many people have MongoDB mugs at home? Nobody, actually, wow. Okay. So we definitely, in hindsight, should have brought some. We're famous for making mugs, but we also make databases. And the topics I'm going to cover is start off by talking a little bit about drivers. A lot of this presentation was lifted from a PHP talk that I gave last year. And then I usually keep it up to date with as the server changes. But I, in everyone's interest, ripped out all the PHP stuff. So this is all pretty language agnostic, as I didn't want to throw that on anyone. But after a note on the drivers, we're going to talk a little bit about schema design, so how to structure so even though Mongo doesn't enforce a schema, it's good to have one in approaching an application for your own sanity. And so talk about some of the trade-offs you can make with schema design, and then look at, and just using the database, how best to use the write operations and the read operations. And then the operations bit will just talk about replica sets for making sure you have disaster recovery. And then sharding, which is a tool that we have for scaling the database, touch on that. And then wrap up with just a thought or two about ODMs, if your language happens to have one, and if you're using it as well. So I had a free time after lunch today, so I went back and I added GIFs to all of the title slides. So hopefully they're somewhat enjoyable. So MongoDB itself, so I'm a member of the drivers team. There's about 30 of us total. And we're kind of divvied up in groups of 2 or 3 per language. So these are the languages that we officially have staff to develop. But there's also a bunch of community-supported drivers for all of you Haskell developers out there, or things like R for doing stats work. So there's languages that if we had staff, we'd certainly focus on them, but there's limited resources how many people we can hire. But in addition to that, we try to enable the community either by, so in the one case we have a meta driver, which is try to be like a living specifications for what a driver should do, because there's plenty of people using Mongo with like new languages. So we actually are sponsoring someone to write a Go driver, but Rust has also popped up recently within the last year or 2, and I'm not aware of, we're not supporting a driver for that, but I think someone is in the community is making one. So we have a meta driver project, which is it actually happens to be implemented in Ruby as a proof of concept. It's unrelated to a Ruby driver, and this is really just a pure implementation of what the specs for a driver should be. And so I'll have the slides up later. Everything in blue here is links, so you can go follow the links as well. But one of the initiatives we're trying to do this year is have a mailing list, extra mailing list, because we already have a number of them. And be more vigilant about putting specs as we develop them. So the 30 of us inside the company that are developing specs for the officially supported drivers, to make sure there's specs for the community to use as well. And that should ideally reduce the turnaround time when we have to implement new features. The community can follow up much quicker if we publish our specs. So as a user of the database, before even updating, the stronger suggestion than keeping the actual database up to date, maybe you want to stick on an older version for some reason. We have some customers that still use the 1.x versions. But it's probably more imperative that you keep your drivers up to date, because these are going to be, the newer versions of drivers will go back and support the older databases. And those are the ones that include probably the more important bug fixes as it pertains to your application. Whereas with the database server, you want the new server maybe for newer features or maybe storage improvements. But in your actual application, having the driver is usually less of a big problem for you to upgrade. So most of our drivers have semantic versioning, which means that the major version is the first version number. So when we break backwards compatibility, that number should get bumped up. And between like a 1.2 or 1.3, we shouldn't be breaking backwards compatibility. So if a driver supports, or if any application supports semantic versioning, you should be comfortable upgrading without expecting anything to start breaking, unless you're going to a new major version. Just a note, the server actually doesn't follow that. It's more like Node.js, where it's like a 2.6 and a 2.8. Those would be the stable releases, and then the odd number in between. So things do break between, or backwards compatibility is lost between maybe Mongo 2.2 and 2.4. And major features are added between those as well. The other parting note I just mentioned on drivers, so I tried to keep all of the code examples to the JavaScript shell, which is, if people are familiar with like SQL shells, it's basically just the command prompt into Mongo. In MongoDB, the shell is a JavaScript REPL, so you can just you can script it like JavaScript. And this is how probably a lot of people, no matter what language you're using, everyone probably uses the Mongo shell to some degree. And JavaScript is kind of a common denominator where most people are familiar enough with it. So all the code examples are going to be using the JavaScript shell. I didn't want to focus on syntax from one particular language. But if we go in the JavaScript shell, I know one of the talks yesterday gave a NoSQL introduction, and it used a lot of the same syntax here. So in the shell, the DB JavaScript variable always points to the current database, and you can kind of jump between them by saying use this database name or use that database name. And from DB, we access the collection, which is like our table. And from there, we usually have methods to do stuff on the table or the collection. So there's, in addition to just the CRUD operations, the reading, inserting, updating, deleting, there's extra commands that we can run. So things like doing MapReduce or running a distinct query. But not every driver has, there's many more commands than all the drivers have helper methods for. So sometimes there's, Mongo has geospatial capabilities, so there's a geoneer command. So you might not find this in every driver. In the case of the PHP driver, we don't have a helper for the MapReduce command. But thankfully, all these things are implemented through a consistent interface. So all the database commands have a consistent interface to execute them. So whether or not there's a helper method, every driver should at least support the ability to run a database command. And it won't have the same syntactic sugar, but you still have the full capability to run everything. And additionally, sometimes the methods in trying to have a consistent, or a small API and not have too many options, sometimes the helpers are actually not as feature complete. Maybe the command has new options that the helper methods don't support. So definitely be familiar with whatever your driver happens to be, whatever the way is to run a raw database command. Get familiar with that and know when you should consider using that. So note on schema design. So with MongoDB, how many people are familiar with basically the concept of a document and the resemblance to JSON? Okay. So yesterday there was some conversation that where it's tempting to just say it is JSON, but there is some slight differences to it. There are extra types added and things like that. But definitely when we work with the JavaScript shell, we're basically writing JSON documents. So one of the things MongoDB is infamous for not supporting, in the interest of web scale semantics, is the inability to do joined queries. So if we're selecting data from one collection, we can get documents and results from that collection, but we can't combine multiple queries into one read operation. So this means that we have to think around this and look at other ways of organizing our data, which might mean denormalizing, which is like keeping the related data local to our documents so that we don't have to go and do those extra queries. And the other two things that we can take advantage of are references, which is basically just storing the ID of a document maybe in the same collection or another collection. And then there's some conventions in play that drivers follow for organizing references. So kind of a structure for what should a reference to another document look like. So maybe if it's in the same collection, you might just want to store the ID, but there's a convention to follow if you also want to store the collection name as well. And with embedded objects, that's when we would probably want to have since in your MongoDB documents, in addition to just your scalar fields and the familiar columns you'd find in a relational database, we can have arrays and other objects as field values. So in that case, it's logical we could take an object that we might want to refer to and just embed the whole thing inside of another document. And that certainly adds to the storage of the document we're embedding it within, but it keeps the data local. So that's an even greater form of denormalizing than just having some related fields. So what this might look like if I had some user documents, and the only thing that MongoDB enforces upon every document in a collection is that there has to be an _ID field, which is just the unique identifier. So it's you already get a unique index just for the collection existing for that. But apart from _ID, you can use the other fields are up to you. So we could have documents that have, you could have a document in a collection where it's the only one that has this special field. And otherwise, in most cases, people like to have a consistent schema though. So in a user document, in this case, I'll store the name, I'll store an array of my friends. I'm just basically going to store, those are just going to be their _ID fields. And one thing in my application, if I'm constantly storing, getting a list of my friends and displaying their usernames, with this data model, I'd have to do numerous queries to get that data. And so at some point, you might say, well, I'm doing too many queries. I'd like to make things more efficient. So a change of schema would be denormalizing the names just and having them local. And so now instead of having an array of strings, which are really just the array of referenced IDs of my friends, I'll change it and just be an array of objects. And those objects will just have the identifier if I want to go and follow that relationship. Otherwise, the data that I need in most of my use cases is just going to be available every time I fetch this document. And certainly the trade-off here is this, as your friends list grows, so does the main document that you're storing on. Yeah, question?
Yeah, quick one. I'm wondering why in the MongoDB there is no eager loading and lazy loading. In the sense, say for example, anyways, the friends, I know the usernames. So if I want to bring back all the collections of the those objects, I should be able to pass a parameter in the rest, and I should be able to get back.
So the question is, would there be support for lazy loading and just knowing that these refer to other things? So this is something that we leave up to. This is where an ODM would come into play. So that's a feature of a lot of, essentially an ORM for a document relation. It stands for Object Document Mapper. So those typically have that kind of logic where you'd have a model class and you'd have your related documents with something that gets lazy loaded. Yep.
With bottom structure, is there a best practice for synchronizing? Because you might have then a record of those friends separately, and so if those friends' names change, is there a best practice for synchronizing?
So, to clarify, the _ID will never change. But in the case when we're denormalizing names here, if Hannes's document, if he decided to change his name, then I would have to make sure, in my application, I'd have to make sure that this is kept in sync. So with any time you're denormalizing, you're at risk of the data coming out of sync. In this case, maybe it's we're not expecting people to change their names often, but if you had things maybe like the most recent 5 friends, and you were denormalizing that every time friends change, you have to keep that updated. Or maybe people delete their accounts, and so I need to remove them from the relationship.
So it's at the application level.
Yes.
Okay.
Yep. A second optimization will be in tandem with denormalizing is to store computed values. So one thing when we were dealing with arrays, MongoDB you can query and calculate the size of an array with the query language. But in things where we're dealing with counts or maybe I want to just keep track of how many friends I have, it's not efficient for me to issue a query with the operator that computes the size of the array at runtime. So an alternative might be to also store alongside that array of friends, to just say maybe a num_friends field. And every time I would push a new friend into that array, I would also increment the num_friends field. So in this case, having these extra fields makes on one point I have, instead of it being something I compute at runtime, I now have a field in place that I can increment and then also index if I wanted to find users with the most friends. Which would be a lot harder to do if I was trying to sort dynamically based on the size of some computed values. A second thing that, so this is a real use case from one of the previous companies. So we were doing user-to-user messaging inside of an application, and there was a library for the web framework we're using that provided this, and it had a form for SQL and a form for MongoDB. And the schema they chose with MongoDB was each of the messages, we basically needed some way to track whether it had been opened or should it show up as like a bright red alert in their inbox. So had it been read by that participant. And the IDs here, in lieu of using strings, these are the object IDs that Mongo uses. It's somewhat like a UUID. So it's just a globally, we can create these on multiple app servers without any risk of conflicting with each other, because it's similar to a UUID in that respect. So these identifiers, we basically had a hash field, or just an embedded object, and the keys were the identifiers, and then just true and false of whether they had been read or not. And so without any idea of whether this might be efficient to query, this is very straightforward to understand. I just look up and see what that user's ID is it true or false? The problem came when we had to index this, because the inside of our document, every path to a field in that document would have to be indexed specifically. So in terms of querying with MongoDB, the is read by participant this ID would be a completely different path to a field than the second user in this and the fifth. So just by having 5 users here, if I wanted to efficiently have this indexed for all 5 of those different queries I might do, I would need 5 total indexes. So a way to revise this was to take advantage of Mongo's ability to index arrays. And so instead of having creating property paths in my document and creating many dynamic ones, by restructuring the way and storing, instead I'm just going to store the IDs of the users that haven't read it, haven't read the message. And so now I could have a single index on an array field, and what MongoDB does for me is index all of the elements inside the array in that single index. And so that's important because there's a limit on how many indexes we can create per collection. And then it's also more beneficial to be able to use the same index rather than many indexes, because that means that that one single index can be kept around in memory. It can be more efficiently handled by the operating system in memory. And so this is one of the refactorings I implemented that made the queries a heck of a lot faster. Another note on if we're dealing with tree structure. So in this case, if we're dealing with maybe like a tag hierarchy or just any kind of maybe like a genealogy or something, the way that documents are structured, we can certainly store this all in one document and just have nested subfields and just go n levels deep. The problem here is that it's difficult to query because if we want to get the entire tree back from MongoDB, that's easy. But it has the same problem of dynamic field paths because based on the depth of the leaves, they're going to have different paths within the document. So just the top level name is the entire tree. Maybe that's the American literature tree. But if I wanted to go 3 levels deep, I might have to do the document.subcategory, .subcategory, .subcategory. And so maybe the leaf I'm looking for is not 2 levels in, maybe it's 3 levels in. So it's an entirely different property path to access in the document. But this is perfectly fine if we were just storing it and receiving the entire tree at once. But if we're dealing with, if we want query flexibility and we want to be able to select the leaves as needed, we might reorganize this and decide to break things up into the individual leaves and have those be the documents that we can query to. And so now the leaf names, we'll use those as the identifiers. And so we already get that free index for _ID. And then we'll just keep track of our parent. And so if we wanted to, we can fetch everybody and just rebuild the structure of the tree. But this gives us more flexibility to query individual leaves. But take this a step further, maybe in our tag hierarchy, where frequently we want to search for everything from a leaf or a node in the tree and everything down within it. So how can we find stuff like under a branch of a tree? So with that, if we took advantage of just storing what our ancestors were, and this is, again, kind of denormalizing, and it brings up the notion of, well, if the tree structure changes, things might get out of sync. But if we had our ancestors in order of who was there, if I was looking for everything under American literature, I can search where the ancestors field is equal to American literature. And even though in most of these documents it's going to be an array field, MongoDB knows I'm querying an array, but I'm saying where the array is a string, so it's going to look for that scalar value inside the array field. So the query language accommodates me. It's intuitive and convenient as what I would expect it to be. And additionally, we still only have to have one. We could just index the single ancestors array. So we'd have the ID index and then the ancestors index for the entire collection. If you're working with analytics and doing things like tracking page views or metrics in your application,
That was 5 minutes, sorry.
I'd recommend John Newmaker has a presentation he's presented at a couple of MongoDB conferences called MongoDB for Analytics. It's pretty easy to just Google his last name and the name of the slides. An example of the schema that he goes through in his presentation, so I'd rather send you to his presentation than rehash this. But he does a couple of things by keeping his field names very short because he creates many, many documents. And so In MongoDB, there is no, your field names are just serialized with the data in your document. So if you like to use field names that are is read by participant, know that it's going to take up a bit more storage. But in his case, he's creating millions and millions of these tiny documents that he's then wants to be able to increment to do counts, so the overhead would be a lot larger. So in his case, he keeps track of these are page views, and then it's maybe these are the total aggregate numbers. And then this is page views for 2011, just the month of February 18th, and then 2 values for that. And so when he does an increment, when a new hit comes in, he can send an increment operation over to MongoDB and update down to this property path. So he'll upgrade 2011-02-18.t, and he'll increment the top level t value in the same operation. And so in his application, he gets a lot of good write performance out of this. By the second thing he does is by on the first day of the year or the first day of the month when he creates these documents, he creates the entire shell of all the fields, even if it initializes them to 0. And so we'll talk about that a bit later, but it prevents the document from growing over time. So since these are always going to be 8-byte integer fields, by creating the entire frame of what the document will ultimately, all the fields that will exist, by creating that up front, we avoid the case where a harmless increment on a new field that didn't exist before makes the document grow, and now we have to find a larger place on disk for it. So that's the other takeaway that he covers in his presentation as well. So the other note is just not to abuse schema flexibility. So you have the ability to have documents not have certain fields, or just create fields at random as you do like a new insert or an update query on a document to just add new fields. So don't abuse this to the detriment of clarity of dealing with your own data. And generally, as you're creating new queries, you should have indexes that service those queries. So just a rule of thumb, as with a relational database, is you don't want to run queries that aren't handled by some index in your application. So some notes to make the most out of your indexes. Certainly kill as many birds as possible with one stone. If you could have one index that services 5 queries in your application, or 6 or more, that's much better than just having one query per, one index per query that your application might do. Because that you're limited in the amount of memory that your servers are going to have, and the amount of MongoDB will limit you to the number of indexes to some sane limit of, like, I believe it's 32 or 64 per collection that you can create. So you want to avoid the case where every query needs a specific index. You could take advantage of compound indexes, which is indexing multiple fields. So if I was indexing the fields x, then y, then z, I could use that 3-field index for queries on x and y, or all 3 fields. It wouldn't be as useful if I was just querying directly on z, because the index is firstly organized by the fields in order. And that's very similar to how compound indexes in a relational database work. When I refer to multi-key indexes, that's dealing with indexing arrays. So having one index and being able to index multiple array fields is a great way to make better use of them. And you can certainly mix these as well. We can index an array field and some other fields as well. We can't index 2 different arrays at once because the Cartesian product would be quite explosive in some situations. But you can mix one array with other scalar fields. The other thing to note is just, as with a relational database, mind your read-write ratio. So every time we're doing writes, if we're changing indexed data, in addition to inserting the data or updating it on disk, we also have to update the index as well. And on the read ratio, if you're a heavy read application, then you probably want a lot more indexes. You're willing to take the hit when you do a write. But if you're doing a lot of writes, you probably want to limit the number of indexes you have so that you're, in most cases, just inserting and writing the bare minimum of data that you're. Yes?
Can we do full text index on fields?
Yes, there, as of 2.4, there was experimental text indexes, and now in 2.6 there is a text index type.
Oh,
so that feature does exist. And then lastly, another note that really none of this is specific to Mongo, but ensure query selectivity. So if you have user documents and you have a is-deleted field, which is false for 95% of your users or 99% of your users, probably doesn't make sense to have an index on that because you're indexing a field that really doesn't help you see much less data. The goal of an index should be to allow us to write off having to go look at data on disk. So we have an index that just still tells us we have to look at 99% of our data. It's really not doing a job at being very selective. And there's no need to be uninformed about this. So we have 2 facilities built in. The first is Cursors are when we do a query in MongoDB, we get a cursor is basically our handle on the results. So with our cursors, we can explain them and ask MongoDB, well, just like running an explain on a SQL query, how would this query run on the database? What are the indexes you would consider? And also maybe tell me how performant are those indexes? Because there's certainly in a lot of cases, your query might, 3 indexes or a couple of indexes might be suitable for your query. So MongoDB is going to periodically, on its own, will just decide which is the index that's fastest to use, and I'll remember that decision for maybe the next 100 queries. And then periodically revise that decision. When we explain, we just ask MongoDB to pretend that you never saw this query before. Tell me exactly what the different indexes would be used, how they would be used, and which would be most efficient. Additionally, there's profiling, which is a mode of that which can you can turn it on for everything, which you wouldn't want to do in production, but there's another way where you can just profile things that take over so many milliseconds. That's perfectly safe to do in production. It just if a slow query were to get through for some reason, it would show up in your slow query logs. So at a hackathon last year, I made a tool that the slow query log ends up just dumping the results to a collection, so you can peruse that later. And last year, I made a little project in PHP called MongoQP, so it's pretty easy to Google for. And it basically runs MapReduce on that slow query output and kind of aggregates the queries, because one of the things when you do a slow query log, you might see the same query that looks the same. Maybe you're searching by different usernames, or some of the values are different, but the actual shell of the query and the fields you're looking by are the same. So I go through and I MapReduce on what is the skeleton of the query. I don't care about the values, but what is the shape of the query, and aggregate on that so you can kind of reduce a whole bunch of slow query profiles and just see what the unique actual queries were. So there's a couple of people using this, and I still kind of maintain it in my spare time. So look at write operations. I'll just wait for okay. So there's 2 different ways to do updates in MongoDB. So insertions are insertions. We take the document, we stuff in the database. When we use atomic operators are what we're doing at the bottom, but I'll show you the first API, which a lot of people start with. And so if we were to do a find query, and if you were in the talks yesterday, hopefully the syntax isn't too foreign. So we do DB users collection find, and we give it a bson document, or it looks JSON in this case. Underscore ID J Mikola, so just where underscore ID is this value of J Mikola. I'm not using any of there's tons of other query operators we can use, but I'm not doing that here. So that'll find the result. This should be a find 1, because find would give us a cursor and I'd have to iterate. So assuming, let's say this was a find 1 instead. So that would either give me back null or the actual document. And so from there, I'll go document, I'll access the friends field, and then I'll push my friend's name, Pablo Godel, into that array, and then I'm going to save it back. And so what save is going to do is just take the entire document it gives me and then write that and overwrite whatever was there previously. So does anyone think why this might be a problem if you were doing this in like a web application? If you were just doing these, I'll write the whole document back to the database.
Is it the versions?
Versions? Close. It would be if you had multiple operations running. Maybe someone submitted a form and they changed one field, and someone submitted another form and changed a different property. So the last one would clobber the previous one. So instead, what we want to do, and what most ODM libraries would do, because they basically, most of the ODM libraries you'll have a model class and it'll just watch and see what properties changed. And when the properties are changed, we want to write that to the database. We just want to write back the change set. So we'll use atomic operators, which is like doing update set specific fields in SQL. So update, we give that, the first argument to update is usually the query criteria. In this case, it's going to take us to exactly one document, but we could do multi-document updates if you like. And then the second one is going to be essentially the payload. So what are all the modifications that I want to do? So one thing you'll notice is $push. We use, so the query language here we have underscore ID, and then with pushing, basically we use the $sign to denote operators. So you would not have fields in your document that start with a $sign. So I lied before, in addition to underscore ID, the other thing we impose on you is not having fields that start with a $sign. But I do think that is the only other caveat. So with $push, that would say I want to push into, and that assumes that I'm going to give it an array field. So into friends, I'm going to push this value into friends. So this is a small example. There's a rich, just as there's dozens of query operators. There's also dozens of different update operators. One of the neat things, since the schema is relaxed, if the friends field didn't exist, I'm trying to push into this field that doesn't exist, so let's make it an empty array, and then stuff pgodal into there. So again, I don't have to think about that when I'm using this API. So note on atomicity, there is no transaction for dealing with multi-document rights. So previous company I worked for, I threw this anecdote out there when we were talking about it yesterday. It was an e-commerce company, and we used MongoDB to store all of the product information because making EAV tables in MySQL is quite hard. And then we used SQL with transactions to do all the actual order stuff. And so we used MongoDB for when it was flexible and convenient, and we didn't use it when it was obviously had limitations where we couldn't do transactions. So don't go into this thinking that you don't force yourself to write the entire application in one database. Use the best tool possible. So that said, we can update single documents. That all happens atomically. So as you're updating fields in a document, no other write is happening at that particular time. And one of the things that version over version that things have been improving drastically from well over a year ago was just getting our granularity of the write locks down a lot better. So I think one of the selling features of 2.8, we're not going to ship 2.8 until it's done, would just be to have document level locking, which is something that people have been waiting a very long time for. So that said, can we query for something and update it atomically? So this is important because between querying for something and updating it, if I was not the case of running an update statement, but if I was like finding a document and then I wanted to modify it, can I do that in one atomic thing so that nothing else comes in between? So with respect to a single document, we do have a particular command for this. And so it's hard to think of contrived reasons why you would immediately want to use this, but one great example is if you were creating like a job queue. So in the case if I was like a library system and we had an unlimited budget, so I hired a bunch of MongoDB developers to make a loan system because I didn't want to hire a librarian. We could have a database in the loans. If a loan request came in, we just create a unique identifier. It might be the combination of who's borrowing it and what the book is. We'll just say it's not pending. We haven't approved it, and it has priority of 1. So maybe important users, if you pay for the special library pass, you get a higher priority. But now my cron job is going to go in and basically mark that loan request and kind of service it. So what I could do is say I'll go find it and I'll just modify it and I'll write it back to the database, but another higher priority thing might come in its place. So by using find and modify, I could pass query the query criteria, so I want something that isn't pending. And the additional benefit here is that I can give it a sort criteria. So this is something that if I didn't care about the sorting, I could probably just use a normal database update. But this allows me to basically do the full amount of a query that find would allow me to, and combine the update statement in one operation. And so this will all just happen atomically, so I'll make sure that the thing I find and the thing I immediately update, nothing else got written to the database in between that. So at that point in time, I did service the thing of highest priority. So note on write concerns, the drivers, we give you the ability to, if you don't care about, if you really want to write data as fast as possible and you don't care about how, if it has errors or not, we have different levels of write concern. Likewise, if you're in a replicated system, you might want to do a write operation and make sure it gets replicated, at least to a second server. So a lot of the write operations, they take a options object, and the older drivers, we had a safe option, which is just true or false. So that obviously was limited because now we're supporting a cluster of servers, so we want to be able to maybe have it acknowledged across 2 or 3 or 4. So now we have a W option. The default is 1, which basically means the single primary server, so the single server that we can actually write to, has to acknowledge that the write succeeds. This is important at the very least to make sure that your unique index is respected. And additionally, if you're dealing with a cluster of servers, you might want to write to, you might not know exactly what the number is, but you would like the majority. And so by writing to the majority, that makes sure that my write operation gets replicated to the majority of them. So if there was a failure and a failover was to occur, I'm guaranteed my data is still there because the majority cast the vote of what servers are still up. So this is the only, at this point in time, other than using a number, majority would be the special symbol that you might use. And there's some other features here if you care about if it's actual imperative data you need to be journaled or synced to disk for whatever reason. There is control over that, obviously at the cost of performance. So I noted before, talking about John Newmaker's presentation dealing with document growth. So every time a document, new fields are added or it changes, if it grows on disk, we have to find a place to put it. And we don't want to have to move it around on disk. That's an expensive operation. We don't want to do that every time the document grows. So when you first insert something, if it is 50 bytes of worth of BSON or a kilobyte of BSON, it'll take up exactly that much space. The first time it grows, we'll move it somewhere and we'll give it some extra breathing room. And over time, the MongoDB will watch a collection and say, well, how often, each time these documents grow, by how much does it grow? And it'll kind of tune, different collections will have what we call a padding factor, and we'll track this independently for different collections. So you might have a collection of documents that basically double in size every time, so they'll have a much higher padding factor. We'll give it more breathing room when it moves. For other collections that really, they grow very minutely, the padding factor could be very slim. So we don't want to apply one number to the entire database. But basically, every time we move a document, we're leaving fragmentation behind, similar to a file system. And so there are routines in place, kind of like maintenance operations, to kind of defrag a database and clean up used space and compact it. But nothing that you would want to run, you would have to basically take the server offline to run that. So ideally, you want to avoid spuriously growing your documents and having them be relocated. And so that's why if it's possible, try and update your documents in place. So in the case of the stats, that was John Newmaker creating that whole frame of the document up front. And good schema design also certainly comes into play here. So reading. So if there's two things, the first is queries should be indexed and know what your working set is, which is the combination of basically how much of my, I might have terabytes of data, but how much of it is regularly accessed. And that's what I should have, I should make sure that that is reasonable to given my memory constraints. Because as we're reading data from the database, we're going to try and keep it around in memory. The operating system will try and keep it around in memory mapped database files. So when dealing with a cluster, we give you a couple of tools. The old behavior, again, was a Boolean option, was do we want to read from secondary servers or not? So slave OK. But now people have more complex situations, so we have the ability to, you could read, by default, we just read from the primary, which is always the same server we write to. We can prefer the primary. So maybe if there's a failover and there happens to be no writable server, but there are slaves available that we can read from. So primary preferred would still allow the reads to happen, but if the primary is there, we'll give that first priority. So these two are certainly gives you the most consistency because you're always getting, or trying to always get the primary. If you can tolerate sometimes reading stale data, and maybe in the sake of performance, or maybe because the secondary server is closer to your application server, you might be comfortable reading for a secondary. And then nearest is kind of makes the decision based on ping time. And then there's a notion I alluded to on the previous slide. There's for tag sets. So if you have multiple data centers, you might want to annotate that certain secondaries and maybe certain primaries, these members are in this particular data center, or this region of the world. So your primary is going to be in one place of the world because there can only be one primary at a time. And so sometimes people would implement something like sharding so they can have a writable server in maybe Europe and a writable server in New York and split their data that way. But when we're just talking about replicating the data, you might still want to have your secondaries and say, well, this is a secondary on my West Coast side and this is a secondary in East Coast. And so my application server, I might want to prefer to read from an East Coast secondary. Or when I do a insert and a write, I want to make sure that my write is replicated to data centers, 2 different data centers. Instead of just saying 3 servers, I maybe want to say it's fine at 2 servers, but I just want it in 2 different locations. So that's where tag sets can come into play, both for writing and reading. So note on JavaScript evaluation, because this comes into play with when we do queries. So there's a query operator called $where. And it lets us give it a little bit of JavaScript. And so as we select the document from the database, we evaluate a bit of JavaScript. So this does serve a purpose if we want to compare 2 fields in the document to each other. Currently, we would have to use the $where and give it. And the JavaScript would essentially look like this.x double equals this.y. It just evaluates the JavaScript. And if it returns true, then it's a match for the criteria. Otherwise, it's false. There's also a facility to, but we could do other things like where if we said this.x double equals foo. There's no benefit to doing that. You might as well just issue a real query that says where the x field is foo. So don't evaluate JavaScript if you don't have to. There's certainly a limit on the server we can evaluate. The JavaScript engine uses V8, which is what Chrome happens to use. So the evaluation is quite speedy, but the server does not run multiple evaluations of JavaScript at once. There's a single lock for evaluating JavaScript. So the question I would ask is, I'm saying JavaScript here, but in any language that you're using, if I was talking to PHP developers and say, would you use eval in PHP? You probably don't want to. There's some use cases for it, but in general, steer clear of going to this solution first. So with MapReduce, which was one of the things talked about yesterday, basically a two-step data crunching routine. So MongoDB does have support for integrating into Hadoop if you want to do MapReduce more efficiently, but if you want to stick to just what's in MongoDB itself, we have the algorithm for MapReduce implemented, and you can send the database JavaScript functions. So there's an allowance there. JavaScript is basically the API for dealing MapReduce within MongoDB itself. But when people need a lot more performance, usually they'll connect it up to Hadoop or some external system and just make MongoDB the storage driver for it. But even before, just because MapReduce is available, don't immediately jump to that. So one of the things that was added about a year ago was the aggregation framework. And so this was a way, previously the actual query language when you're doing find operations doesn't have the ability to do groups and aggregates. And so MapReduce was, going back to the 1.x versions, was really the only solution for that if you wanted to do it all within MongoDB and not in your application code. So one of the things that was added recently was the aggregation framework, which is kind of like if Mario is a document, he's going between different aggregation operators. So we basically have a pipeline of operations. So this is, it's actually an aggregate command, but I'm just going to use the helper method here. And so the aggregation framework, instead of writing a map JavaScript function and a reduce JavaScript function, I feel this is a lot more intuitive. The algorithm is basically, it's a pipeline of different operations. There's 7 different ones. The ones we're seeing here is sorting. Unwinding is basically unwrapping an array field. And then the $group is is one of the aggregation steps. So basically, when we start off this pipeline, a bunch of Marios goes in. Those are all the documents in our collection. They enter the pipeline. And every time they go through an operator, so with sort's going to suck up all the documents and then emit them to the next pipeline operator in order of whatever the sort might be. In the case of unwind, a document comes in, and maybe it has a subjects array with X and Y. So then 2 documents will be emitted, and the subjects is no longer an array. Now it's just the individual values. So we kind of replace the array with its values. And with $group, that's the operation where this will suck up documents and then ultimately emit buckets based on, it'll emit different documents. So the books might come in, and then group is going to then emit documents that have an ID that is whatever the subject was, and then count happens to be a computed field. First graded happens to be a computed field as well. So there's a rich query language of operators that you can do with this as well. But the main things in the aggregation framework are sort, limit, skip, which are familiar query operations. $match, which is basically the find criteria. And then unwind and group are the other 2 main ones as well. So this is, you can easily find this in our documentation. There's a lot of intuitive examples for it. But I find just maintaining something like this versus having map and reduce JavaScript functions, for a lot of the ways, maybe 90% of the cases, what previously people were doing in MapReduce could be done in aggregation framework. And the benefit here is that this is an actual part of the raw query language, so we're not evaluating JavaScript for this, so it's a lot more performant as well. So note on operations. Just wait for that to finish. It's adorable. Okay. So the different players in a MongoDB deployment. So we have the application, which hopefully you're writing, and the driver that you're using for your language, and then the database servers. So we have MongoD. When you download MongoDB, there's the MongoD process, which is the actual database server. And then if you're in a sharded cluster, we have MongoS, and you can think of that as kind of like a load balancer or an HA proxy to MongoD servers. So So one of the nice things is that the drivers don't have to know about sharding or don't have to explicitly handle a whole shard cluster. They can talk. It's the MongoS is the job that intercepts a query and will take care of divvying it up, sending the query to the particular shard server or shard cluster that has the data, and giving it back to the driver. So it keeps the drivers quite a bit simpler. So with MongoDB, there's if you're running a standalone web server, a standalone database server, you might just run it as MongoDB. There's the REPL set option. So if you're running multiple Mongo DBs and you want them to replicate the same data, you'd start them each with the REPL set option and give it the same name. And then when you load them up, you give them each a common configuration so they can see each other. And then one of them will become the primary, the other ones become secondaries, and it's a nice big happy family. Additionally, there's a second type. So with primaries and secondaries, those both store data. There's another node type called an arbiter, which is basically a voter, or an observer of the other. So it's a member of the replica set. So maybe in a case where you had a replica set of 3 members, primary, a secondary, and an arbiter, we wouldn't want to just have 2 members, because then if one dies, the other one is not the majority. So we always want to have a majority to vote for failover situations. So that's exactly what the arbiter does. It's kind of just watches. It doesn't store any data, so you can run it on the resource demands are much lower. You can run it alongside a web application server or something like that. And its goal is just to vote when necessary, watch other people that might disappear. Yep.
Just a comment on that. We have 2 data centers in our arrangement, so that we have our, I guess, voting member. It's just exclusively that in one. But if we lost an entire thing, we found that we would also need a voting member in the other side, because then there would be a tie, basically.
Yes. When you have 2 data centers, usually you'd pick a third place, or maybe like a cloud-hosted solution to put the external observer, because otherwise you don't want to have a majority in one data center.
Right.
In the interest of having good failover. So, I'm going to hold off on the questions just to get through the rest of the slides. I'll certainly stick around after. So just to compare replication and sharding. So replication is not about scalability, even though we can send queries to secondary servers, but it's mostly for data safety and making sure that we have our stuff backed up. Sharding, when we actually talk about scalability, sharding allows us to scale because we're actually partitioning our data and reducing the ratio between the amount of resources on the system and the amount of data that's stored there. So just to cover what this looks like. With replication, we always want an odd number of members, and hopefully I drilled that in enough with the concept of when we vote, we need a majority to decide, well, who's the survivors after a failover event. And then we have the ability I mentioned to tag nodes so that we can say that they're in certain data centers, just annotating them for accounting purposes, or also we can use them for reading and writing to make sure that we hit certain data centers. And there's other options as well. We could have nodes that are purposely an hour or 2 behind. So in case a fat finger happens to delete your entire database, it doesn't get replicated immediately. We'll have one node that is just essentially the state of the replica set, but 2 hours ago. So in an emergency situation, you can go to that node and kind of do a live backup of the data. There's hidden members that you might want to have a secondary that's just used for backups, but your application server doesn't ever have to see. And then priority as well. Priority is basically, if the nodes are all healthy, the one with highest priority should become the primary. So you'd probably want to give that to the one with the best resources. And then the tag sets I mentioned can come into play with write concerns. With sharding, each shard could be a single MongoDB process, or ideally it's going to be a replica set, just for good data redundancy. They could be tagged too, so we can tag shards. It's a little bit different than the replica set tags, but if you're interested, you can. That's covered in our documentation. But sharding, if you're deciding to go this route, and this probably applies to relational databases as well, picking a shard key or partition key, if you're familiar with that term instead, is the most important decision, because it tells us from when our data is being inserted how it's being split up. So in MongoDB, the shard keys should not change for the lifetime of the document, because where the document is originally placed, everything in that range of shard keys, we should know where that is. We don't want to go and update shard keys on documents, because then they'll end up being in the wrong place. So at the time we insert a document, the shard key should be, assume that's going to be an immutable value. And then certainly over the course of the cluster, MongoDB is going to try and balance things. So it might relocate the document, but we don't want to allow update queries to go through and just like deform the shard keys of all the documents in the database. Like if we decide to set all documents shard keys to 1, now MongoS's whole concept of, well, these are the ranges of shard keys, this is where I go look for certain documents, no longer applies. So that's why the shard key is an immutable field. So picking a good shard key to make sure that you are able to, that you have the ability to have documents be selected and split up so that we actually do have different chunks that we can relocate when we try and balance the shards is very important. So an example of what this might look like in sharding. So if we're using something like a incrementing value, the object IDs happen to be auto-incrementing or maybe a time-based value. In a shard cluster, and there's a parallel here to how this relates to index usage. If we're constantly inserting documents with a incrementing value, they're always going to kind of go to the same shard because the range of maybe yesterday to positive infinity is like the upper range, and then we have previous chunks. Those are just going to keep going to one shard. It'll eventually fill up, and then it'll carry over. But if we're using a completely something like a hash as our shard key, something completely distributed, then we could be inserting and hitting all the shards, basically distributing the write load perfectly. This may also not be ideal because maybe you want you want your writes to kind of be consolidated in some places. So usually a trade-off is to have some bit of incrementing and some bit of distribution as well, so that we can make use of a bunch of our shards, but not try and send all of our inserts completely different places every time. So as this relates to indexing, so when we have indexes and we're doing queries on completely distributed values, we're accessing all parts of the index. And then if we're always accessing one side of the index, so maybe if you're Twitter, the tweets are constantly increasing. If you're always accessing tweets in the most recent bucket of 5 million or something, maybe that is everything since yesterday, you're always going to be accessing part of the index. So usually that's the overlap between the way a shard cluster might get utilized for write performance, and then also on the flip side, when we read from indexes, what part of the index in memory do we have to access? So we might be indexing a lot of data, but we might also only be querying a portion of it. So that constitutes that's part of our working set, essentially, of the data that we have, how much of it is actually hot that's being accessed. So if you're using sharding and you're not replicating, you probably are doing it wrong. On the flip side, if you're using replication and considering sharding, or maybe you are sharding, I would definitely do replication before you decide to start sharding. A note on data, RAM, and disk. I'm not going to go too much. I'll jump right to the last slide to explain here. But MongoDB will memory map all of our database files into a virtual address space. And when we access things frequently, we're hitting physical memory. And when we access things that happen to miss, we have to go to disk, and then that will evict the least recently used thing in physical memory and then fill it back in. So I'm not going to bore you with a study on how memory mapping works. But this is what the importance here, certainly with the access time, comes into play when we're dealing with our working set. If we're constantly missing memory and going to disk, we're inviting a much worse database performance. So the things are ideally meant so that your working set should be able to be fitting in memory. So an example from a previous company of what this looked like on an EC2 cluster, we had about 8 gigs of memory, and our just the size of our indexes, never mind the actual data that was stored in the collections, was about 9 gigs. So we were expecting plenty of page faults, and every now and then this might manifest itself. You'll do a query, and it happens to take an exorbitant amount of time. You run the query immediately again, and it's instantaneous. That's because the first query happened to do a page fault, and now when you run it immediately the second time, it happens to already be in RAM, so it's a lot quicker. So if you see a situation like that, there's stats in MongoDB. If you're using our MMS service, which is a free monitoring service that gives you graphs and things, you can track page faults and keep tabs on that. So an example of what sharding does on a single server, this is why replication doesn't help us scale. If we have a single server with so much RAM and that much data held, we have essentially that ratio in our working set. We have a higher chance of our working set filling up. But when we split the data across, we're now storing a third of the data. We're getting closer to the ratio where we have more RAM per data, essentially. And so this is where the scalability of our resources comes into play. If this was just replication, we'd still have 300 gigs of data and probably the same working set for 90 gigs of RAM. But this reduces that ratio and brings us closer. And this also means that these shards can then be more commodity hardware instead of where we might have to pony up for a more expensive EC2 instance for the previous one. So a parting note on ODMs. Great tools, but it's easy to use them incorrectly. So some notes, the benefit with ODMs, if you're using the raw driver, you get back basically maps or associative arrays or dicts in Python. ODMs let you work with actual classes and models in your application. And one of the great things when we were using Mongo and SQL side by side, the previous company, we use the same model classes to store them in MongoDB as well as SQL. And the same model classes just had different metadata mapping it to Mongo fields and metadata mapping it to SQL fields. And so the ORM and the ODM happened to use the same PHP classes, which was great. Typically, the ODMs get great framework and library integration, particularly if you're using like a full stack framework, similar to how like if you're using Rails, you have active record at your disposal. A lot of the ODMs have nice bindings to their particular frameworks. They can definitely accelerate application development. From the get-go, you involve creating your model and creating your schema, which is probably a better place to start than just inserting stuff into MongoDB and then worrying about it later when your queries are not performant or you find documents have, at some point last year, you decided to insert completely different documents in the same collection. And MongoDB wasn't going to complain about that, but now you weren't using a model from the get-go. And the other thing they do is abstract the database layer. So one of the things that I work on an ODM for PHP, Doctrine, and we put effort into, at some point between MongoDB 2.4 and 2.6, which just came out last month, some update syntax slightly changed. They added some more stricter validation. So now update operators, some of them that were, some of the operators now just have stricter warnings. We'll get back an error where it previously should have, but it never did for the last couple of years. So the ODM is not something to fix in the driver because the driver doesn't really care about the queries you run. It's just the job to send that to MongoDB. But with the ODM, it watches your documents change, and then it goes and creates the update statements from MongoDB. So in the ODM, I added logic. If I'm talking to an older version of MongoDB, I know I can create this kind of query. Otherwise, I have to create a new kind of query. In your application code, that would be something that you would have had to handle directly. But this is a caveat because this is a reason where the horror stories of people picking up ORMs or picking up ODMs and not really understanding how the database works at all. So the parting quote from Martin Fowler, maybe the ODMs will handle 80–90% of the work, but it's not an excuse to be ignorant of how the database functions. And so he's talking about relational, but obviously any database. So that about wraps it up. I'll stick around outside for questions. If you have any feedback for me, the joined in is 11191. And we'll do the questions outside so you can wrap up. All right, thank you.